morning, everybody. It's fantastic to see lots of you here, and also hello to the people who are not in this room. So my name's Vicky Neale. Just so you have some idea who I am, I'm a lecturer here in the maths department, so I spend some of my time teaching undergraduates. This year I was teaching the first year linear algebra course, in fact, in this room. There are not quite so many first years as there are of you today, so they have a bit more space to spread themselves out. I spend some of my time at Balliol College. I'm one of the maths tutors there, so I get involved in teaching students and supporting them individually. And then I spend the rest of my time working on public engagement with maths, which means a variety of projects. My instructions from James today are that I have half an hour to tell you about the whole of pure mathematics. So we'll see how that goes. So when I'm lecturing the linear algebra, the format is kind of, I write notes on the board slowly and carefully. They're also online notes, but all of the details on the board, and we have careful definitions and theorems and detailed proofs. And this is not going to be that kind of talk, because I've got half an hour for the whole of pure mathematics. So what I want to give you is a flavour of some of the ideas that come up and sort of give you a bit of an idea of how they link to courses that we currently offer in our programme. And I thought I'd start with an equation. And as you know, maths is not all about equations, but equations are definitely important in mathematics. So the equation I thought we'd start with is y squared is x cubed minus 2, which is a nice friendly sort of equation. And I'm particularly interested in whole number solutions to this equation, integer solutions. Integer just means whole number, positive or negative or zero. Integer solutions to this equation. So as I'm talking, you might notice solutions possibly, but somehow we need to make sure that we find all of the solutions. So we're going to have to do a little bit more than just spot solutions. And experience suggests that one thing that can be helpful in this kind of situation is to think about numbers being odd, numbers being even, that kind of thing. So let's see what happens if y is even. So if y is even, then x cubed, which is y squared plus 2. So if y is even, then y squared is even. So y squared plus 2 is even, so x cubed is even. And if x cubed is even, then x is even. Because if x is odd, and I cube it, I get an odd number. So if the cube is even, the original number must have been even. So if x is even, that means that x cubed is a multiple of 8. Because if x is even, it's 2 times something. X cubed is 2 times something times 2 times something times 2 times something. So it's divisible by 8. But x cubed, we know, is y squared plus 2. So y squared plus 2 is a multiple of 8. But it isn't, because y is even, so y squared is a multiple of 4. Y squared plus 2 is not a multiple of 4, let alone a multiple of 8. So what that tells us is that it's not possible for y to be even. There can't be any solutions when y is even. So this is good, right? We just ruled out infinitely many possible solutions right there. And that just leaves us with the remaining infinitely many. OK, that didn't go as well as I'd hoped. So this says y must be odd. And I don't now have some clever kind of trick up my sleeve for showing that y can't be odd, because y can be odd. There are solutions when y is odd. OK, so we need another plan. This is how maths is, right? So sometimes you get a maths problem, and you look at it, and you sort of know how to solve it. You kind of know what techniques, what ideas. You know, if I apply these tools carefully and accurately and work through systematically, I'll come up with the answer. And that can sometimes be kind of satisfying. But for me, those are not the most interesting maths problems. For me, the most interesting problems are the ones where you look at it and go, not sure. I've got lots of tools at my disposal, but which ones might be relevant? Which branches of maths might I need to draw on to help me to solve that problem? And when you're in that kind of situation, you have to be prepared for the fact that the first thing you try, or the first 10 things you try, might not work out. So you have to be willing to kind of put pen to paper, try something. Oh, OK, well, that didn't help. We still learned something, but OK, it didn't solve the problem for us. So we need another idea. And my other idea is going to involve thinking about the equation in this rewritten form. So I wrote it in this form at the top for a reason. I'll tell you why later. But let's think about it in this rearranged form. X cubed is y squared plus 2. Because now I have a plan. My plan is to take y squared plus 2 and factorize it as a difference of 2 squares. And now some of you are looking slightly anxious, possibly because it's not a difference and they're not both squares. But I think we should be open-minded, because if I rewrite this as y squared minus minus 2, then it's a difference. And if we tell ourselves minus 2 is a square, it's a difference of 2 squares. And I can factorize this just fine. It's y plus the square root of minus 2 times y minus the square root of minus 2. And now some of you look as though you might be having a moment of existential crisis, because I've just written the square root of minus 2 on the board. Please don't have an existential crisis. I promise it's all fine. What do I mean by the square root of minus 2? Well, different question. What do I mean by the square root of 2? What I mean by the square root of 2 is there's a positive number, and if I square it, I get 2. I think that's all I know about the square root of 2, in fact. Anything else I may think I know, like it's 1.4, whatever, I deduce from the fact that it's positive, and if I square it, I get 2. What do I mean by the square root of minus 2? It's an object that, when I square it, I get minus 2. So what we can do here is, instead of just working with the nice, warm, friendly, cuddly integers, go into this brave new world where we have numbers of the form integer plus an integer times the square root of minus 2. Well, the square root of minus 2 is this slightly mysterious thing, but any time we see it square, we'll just replace it by minus 2. Now, my guess is that some of you have met complex numbers and some of you haven't. I know it depends which order you do topics at school or college. So if you haven't met complex numbers, please don't worry, it doesn't matter for this talk. Go with the flow, it's all good. If you have met complex numbers and you're wondering why I've written the square root of minus 2 rather than root 2 times I, the answer is, it wouldn't be wrong to do that, but this is the convention in this branch of maths, is that we write numbers in this form. So we're looking at numbers of the form integer plus integer times the square root of minus 2. It's really not clear that that is a good idea for solving this problem, because I've taken a nice friendly equation, looking for nice friendly solutions, and turned it into something looking a little bit more alarming. But in the absence of any other ideas, we may as well go with it. And when you think about it for a bit, you discover that y plus the square root of minus 2 and y minus the square root of minus 2 have highest common factor 1. I'm going to record that using this brilliant phrase, it turns out that, which means I'm not going to tell you the details. It turns out that y plus the square root of minus 2 and y minus the square root of minus 2 have highest common factor 1. Proving that takes 5 minutes of algebra. I don't have time for 5 minutes of algebra. In the course of that proof, though, we use the fact that y is odd. So this thing up here, which felt like a dead end, it felt like, oh, that didn't work. Actually, we learned something useful about the problem that helps us later on. So when you're working on a problem and you try something, it doesn't work out, don't get cross and throw it in the recycling bin. Hang on to it. It might be useful later on. So what's going on here? We've got two numbers with highest common factor 1 that multiply to give a cube. If that happens in the ordinary integers, if I've got cube equals product of two numbers with highest common factor 1, each of those numbers individually must be a cube. So we can use the same kind of idea here to say that y plus or minus root minus 2 must be cubes. And it doesn't matter which we focus on. Let's just look at one of them. So say y plus the square root of minus 2 is a cube. And a cube in this world means a cube of a number of the form a plus b root minus 2, where a and b are ordinary integers. And now we can just multiply this out, and you can do that probably better than I can. And algebra in public is not my favorite activity, but let's give it a go. So I think this is a cubed plus 3a squared b times the square root of minus 2 plus 3a b squared square root of minus 2 squared plus b cubed times the square root of minus 2 cubed. It's really not clear this is making the problem better, is it? But we can tidy up, because remember the deal is anytime I see the square root of minus 2 squared, I can simplify. So let's do a bit of tidying up. This is a cubed plus 3a squared b root minus 2. So I get a minus 2 here, so I think this is minus 6ab squared. And there's a minus 2 lurking in there, so I get minus 2b cubed square root of minus 2. And now I'm going to tidy this up so that it's written in the form integer plus integer times the square root of minus 2. So this is a cubed minus 6ab squared plus 3a squared b minus 2b cubed times the square root of minus 2. So now I have a number of the form integer plus integer times root minus 2 being equal to another number of that form, and the coefficients have to match up. So it must be the case that y is equal to this bit, and this is the coefficient of root minus 2, which here is 1. So in particular, we get that 1 is 3a squared b minus 2b cubed. And now, for the first time, I have a glimmer of hope that we might be making some progress, because I just noticed that we can factorize this. So this is b times 3a squared minus 2b squared. And the reason I'm pleased about that is that I've now written 1 as a product of 2 ordinary integers. And it's really hard to get 1 as by multiplying together 2 whole numbers. They have to be 1 times 1 or minus 1 times minus 1. So we discover that b has to be plus or minus 1. We didn't want to know about b, we want to know about x and y, but we'll come to that. We can work out a because 3a squared minus 2b squared must also be plus or minus 1. And when you solve, it turns out that that means that a must be plus or minus 1. And now we can go back here because we know that y is, this part. So we discover that y is a cubed minus 6ab squared. And now I've got 4 cases to substitute in, but I'm a mathematician, so I'm kind of lazy. So rather than doing 4 cases, I'll notice that this is a times a squared minus 6b squared, because a squared minus 6b squared, it doesn't matter what case we're in, works out the same either way. So we get plus or minus 5. And if we go back to the original equation, that tells us that x is 3. And so we discover that the solutions are 3, 5, and 3, minus 5. And I know those numbers are small enough that I'm sure that some of you spotted those. And hopefully, if you spotted this one, you might have spotted this one as well, because the original equation doesn't care whether y is positive or negative. So we expect them to kind of come in pairs like this. The important thing about what we've done here is that it shows that those are the only solutions. Otherwise, well, maybe there's some solution with 150 digits we haven't thought of yet. This shows that these are the only solutions. Good. I have 2 confessions to make. I'm just wondering in which order to confess. Okay, first confession, this is 3rd year undergraduate material. Did I mention that? So if you didn't follow the details, don't worry. I didn't give you all the details, and this is stuff that comes up in a 3rd year course called algebraic number theory, so don't worry about if you didn't follow the details. The second thing is that I slightly cheated. But let me tell you where I cheated, because it's quite subtle cheating, and it's quite interesting cheating. The cheating was there. So to tell you about the cheating, I want to talk about Fermat's last theorem. Have you heard of Fermat's last theorem? Some people have heard of Fermat's last theorem. Let me write it down, because it's hard to guess how it's spelt from the way I say it. Fermat's last theorem. So back in the 17th century, Fermat was thinking about this equation, x to the n plus y to the n is z to the n. And Diophantus, the ancient Greeks, knew about this equation when n is 2. This is the familiar equation when n is 2. This is a familiar equation for the sides of a right-angled triangle. And we know that there are whole number solutions. People who write maths textbooks know that 3, 4, 5 is a right-angled triangle, and 5, 12, 13. 3 squared plus 4 squared is 5 squared, and so on. And the ancient Greeks could find all of the solutions to this equation when n is 2, and it's a beautiful problem. I recommend it. Fermat said, well, what happens if n is at least 3? Can we somehow generalize these beautiful ideas and think about what happens when n is at least 3? And if n is 3, for example, you get some not very interesting solutions, because 1 cubed plus minus 1 cubed is 0 cubed. That's not very interesting. So we're interested really in solutions where x, y, and z are positive whole numbers. And Fermat claims that there were no solutions to this equation in positive integers when n is at least 3. And he claimed to be able to prove it, but didn't provide any evidence of that. I don't really know why it got called a theorem, because he didn't provide any evidence that he could prove it, but there we go. In the 19th century, mathematicians had this beautiful plan for proving Fermat's last theorem. Here is a very high-level summary of that strategy. Okay, ready? So you take x to the n plus y to the n, you throw in a complex nth root of unity, whatever that is, and use it to factorize x to the n plus y to the n as a product of n linear factors. This is the same kind of idea as throwing in the square root of minus 2 to get a difference of 2 squares. So then you've got this product of n linear factors being equal to z to the n, and you mumble a bit about the linear factors having highest common factor 1, and argue that individually that means they must each be an nth power, and then you get a contradiction. Just like that. And that was great until somebody pointed out why it doesn't work. And the reason it doesn't work is really subtle, and it's to do with this property of unique prime factorization. In the integers, if I pick a whole number bigger than 1, I can write it as a product of some primes. So if we pick like 12, we can write it as 2 times 2 times 3. It's a product of some prime numbers. Importantly, there's only one way of doing that. I mean, maybe some of you would write it as 2 times 3 times 2, or 3 times 2 times 2, or it doesn't matter which order you put the factors in, but you have to use the same pool of prime factors. And we call that the uniqueness of prime factorization. And that's not just true for 12, that's true for any positive whole number. And I know that's true because it's a theorem, we can prove it. It turns out that in some of these settings where we're trying to generalize the integers, where we throw in a complex nth root of unity or a square root of that or something, we have something that behaves a lot like the integers. We can add, we can multiply, we call it a ring, but we don't necessarily have to have unique prime factorization. And if you don't have unique prime factorization, then the argument, here's a product of n things with highest common factor 1 that's equal to an nth power, therefore they're all the nth powers. That doesn't work. You need unique prime factorization in there. And it turns out sometimes when you throw in a complex nth root of unity, you don't have unique prime factorization. So this proof strategy doesn't work, so they didn't prove Fermat's last theorem in the 19th century. And I guess at that point, mathematicians might have gone, oh, it's really hard, I give up. Mathematicians are very resilient people. And in fact, 150 years of modern algebraic number theory has arisen from trying to understand what's going on here. How come the integers do have this property, which I think almost hadn't really been appreciated until they discovered it failed in these other settings. So how come the integers do? How come some of these other settings don't? How can we tell whether this setting does or doesn't have this unique prime factorization property? What can we do about it if it doesn't? So our second years who do the rings and modules course start to learn about some of this because we're talking about rings here, start to explore unique prime factorization. And that then feeds on into the third year algebraic number theory course, which extends those ideas even further. So in fact, it turns out that if you throw in the square root of -2, you do have unique prime factorization. So in fact, this does work, but there's a little bit of work to do to prove that, sort of. So I'm not really cheating, I'm just not telling you about some of the details. So just to finish the story of Fermat's last theorem, for those of you who are not familiar with it, it has now been proved. It was proved in the mid-1990s by Andrew Wiles and building on work of predecessors, which is why, of course, we're in the Andrew Wiles building today. So he's one of my colleagues. He's got an office upstairs. So, okay, so we know about integer solutions to this equation. What about real solutions to this equation? So we could draw some graphs. Let's try sketching graphs. This is a fun thing to do. Let's warm up. Let's try sketching a graph of y is x cubed minus 2. So y equals x cubed looks something like this. So y equals x cubed minus 2 looks something like this, where this is minus 2. And I'm not fantastic at drawing cubics, but it's just a sketch, so that's fine, something like that. So what happens if instead we try doing y squared equals x cubed minus 2? Have you tried sketching graphs of y squared equals some function of x? You should try it. Really cool things happen. So y squared isn't negative. So anywhere over here where x cubed minus 2 is negative, we're not going to get anything over here. When x cubed minus 2 is positive, we're going to get two values because this equation doesn't mind whether y is positive or negative. So we expect symmetry about the horizontal axis. And this graph is going to kind of stretch depending on whether x cubed minus 2 is less than 1 or more than 1, whether it gets bigger or smaller when you square. And it turns out what you end up with is something that looks a bit like this, which is kind of intriguing. And this is an example of an elliptic curve, which is a confusing name because they're not ellipses. So an elliptic curve is something of the form y squared equals a cubic in x. And actually, there's a nice link back here because when Andrew Wiles proved Fermat's last theorem, elliptic curves were a key part of that. So if you haven't seen the BBC documentary about this, you should totally go and Google BBC iPlayer Fermat's last theorem. It's a 1-hour documentary. It's a bit over 20 years old now, but it's fantastic. You should watch it. If you have other cubics, you can have other shapes of elliptic curves. So let me show you some of the kinds of things that can happen. So one thing that might happen is that my elliptic curve goes up and then it turns around, but it doesn't get back to the horizontal axis, and then it turns around again. So I could have a cubic like that. And the corresponding elliptic curve looks something a bit like this. That was supposed to be symmetric, and it's actually not a bad effort, so I was just having a moment to be proud of it. My cubic might cut the horizontal axis 3 times, And in that case, the elliptic curve kind of falls apart into pieces, and you end up with something maybe looking a bit like this. It's kind of intriguing. So this all starts to link up with an area of maths called algebraic geometry, and we have a third-year course at the moment called algebraic curves. So algebraic geometry builds on this idea that Descartes is famous for Cartesian coordinates, other people as well, that you can take an algebraic equation and turn it into a graph, as we did down here, turn it into a problem in geometry, or you can take a problem in geometry and turn it into algebra using coordinates. So algebraic geometry kind of takes this idea of, well, how can I use tools from algebra to answer problems in geometry? How can I use tools from geometry to answer problems in algebra? What are the parallels between these areas? And that's a really fruitful avenue for exploration. Okay, so we've thought about integer solutions, we've thought about real solutions. Let's think about rational solutions. Why not? So a rational number means a whole number divided by a non-zero whole number, so fractions, if you like. And this is really exciting because if you take two rational points on an elliptic curve, meaning both coordinates are rational, you can add them and get another one. So if you have a nicely behaved elliptic curve, you could take a rational point P, so both its coordinates are rational, they're both fractions, and I could take a rational point Q, and then I add them. And the way that I add them is that I draw a straight line through them, which by a miracle of mathematics intersects the curve just once more. And that's not the answer. We then reflect in the horizontal axis, and that's the answer, and we call that P plus Q. And it might feel a bit odd to call that addition. In what sense is this addition? We're sort of doing something quite geometric working with this curve. But it turns out that it behaves in the same way as addition of normal real numbers in various useful ways. And this is an example of what happens in university, this process of abstraction, which comes up in algebra all the time. This is super important. So you notice the same phenomenon happening in seemingly disparate parts of mathematics. And you go, well, what do they have in common? What is the underlying structure that brings those together? Because if you can then isolate that structure and prove theorems about that structure, that applies to all the examples you've noticed and all the examples you haven't encountered yet. So in fact, the rings that I mentioned earlier on is an example of that process. The structure of choice here is the group. So you find this going on with addition of real numbers. You find it going on with symmetries of an equilateral triangle. You find it going on with multiplying invertible matrices. There's lots of these kind of examples of groups. So what properties does a group must have? I'm not going to list them all. One important property is that there has to be a point that behaves like 0. We call it an identity. It doesn't change it. So here, we need a point 0 so that when you do p plus that point 0, you get back p again. And the point 0 turns out to be the point at infinity, which I can't draw on the whiteboard because it's at infinity. So to make sense of the point at infinity in a precise way uses ideas from projective geometry. That's the second year optional course. So you make sense of this point at infinity, and it turns out that looking at elliptic curves using projective geometry is really nice. That also ties in with this algebraic geometry. This might all seem quite abstract. Actually, it turns out that rational points on elliptic curves, as well as having intrinsic properties of mathematical interest, are also useful for cryptography. So very roughly speaking, the idea is that if you pick a point, a rational point on a nicely behaved elliptic curve, you can add it to itself lots of times fairly easily. So if I give you a point p, you can work out 7p fairly quickly, especially with your computer. If I tell you that this is 7p, it's quite hard for you to work out what the original point p was. And that asymmetry is what makes this kind of tool useful for elliptic curve cryptography, for it's a type of private key, public key cryptography. So people studying cryptography are thinking about rational points on elliptic curves. They're also thinking about what's going to happen post-quantum computers, because quantum computers are going to be able to solve some of these problems too quickly for our current cryptographic techniques to be robust. So post-quantum cryptography is a hot topic. Okay, so we've thought about integer solutions, we've thought about real solutions, we've thought about rational solutions. We should think about complex solutions, right? Why not? So here we're interested in where x and y can be complex numbers. And now it gets quite hard to draw on the board because x is in some sense two-dimensional and y is in some sense two-dimensional. Now I don't have enough room to draw the elliptic curve, but it turns out to be a torus, a donut. It's a sort of surface with a hole in it. How can we possibly know that it's a torus, it's a donut, it's a shape with a hole in the middle of it, when I haven't even bothered to draw it on the whiteboard? Well, we can use ideas from algebraic topology to help with that, geometry of surfaces, to make sense of what's going on here. So algebraic topology gives us powerful ways to distinguish, even in many dimensions, between something that looks like a beach ball with no holes and something that looks like a donut with one hole and something that looks like a pretzel with more holes and so on. So we can use these kind of ideas to discover that it's a torus. And one powerful tool for tackling elliptic curves in the complex world uses the Weierstrass P function, which has its own P written in this special font. My P normally looks like this. This is the P for the Weierstrass P function. And the Weierstrass P function is defined by a doubly infinite series. And now you should feel very scared, because adding together infinitely many things is a pretty risky business, and adding together infinitely many things in two directions is kind of terrifying. But in first-year analysis, we make sense of these things. What does it mean to add together infinitely many things? So maybe you've come across an example where you can add together infinitely many things and get a sensible answer, like 1 plus a half plus a quarter plus an eighth plus a 16th and so on. It's an example of a geometric series. You add infinitely many things, you get a sensible finite answer. We say the series converges. But if you're careless, you add together infinitely many things, it doesn't make sense. If you do 1 plus a half plus a third plus a quarter plus a fifth and so on, that's the harmonic series. It doesn't converge. You don't get a finite answer. It diverges. So in first-year analysis, we're looking at these ideas of, well, what does it mean to say that a sequence converges or a series converges? What tools do we have for looking at a series and going, yup, it converges, or no, it doesn't? Analysis also includes things like, when we do differentiation, we sort of want to take a limit. What precisely does that mean? So getting the logical, rigorous foundations of that precise, which is a really satisfying thing to do. What is the link between differentiation? How do we formalize that? And once you've done first-year analysis, then you can do second-year complex analysis, which is like complex numbers meets calculus, but is much more beautiful than that makes it sound. It's full of theorems that are really surprising, theorems that shouldn't be true, but somehow are because of miracles of complex analysis. And you look at complex analysis of these doubly infinite series, and you've got these tools for making sense of it. So you can make sense of the Weierstrass P function, and you can show that it satisfies a differential equation that starts to have the form of an elliptic curve. So you can tackle questions about elliptic curves by relating back to the Weierstrass P function via this differential equation. I could keep talking about elliptic curves, but I think that I have to stop because you have like another talk or something. I hope that's given you a bit of a flavor of some of the topics that come up in pure maths at university, and I hope you enjoy the rest of your day. Thank you very much.